next to me, all we see a new face. This time around, this is the face of Aleksey Ragozin. Hi. Alexei tends to be focused on one thing, if not fixated. He is fixated on profiling. Anyone ever attended Alexei's talks? Yeah? You remember it's hardcore, very hardcore, the hardest of course. You try to brace yourself, and then you still have to rewatch these videos several times before you understand half of it. How about today, Lyosha? Well, I thought I was telling people the simplest things, you know, profiling 101. And today I also wanted to share with people this bit of information that's not just about Java, but want to tell them how profilers work in basically all languages. Okay. Usually when you have questions about profiling, whatever questions, you have to call Lyosha. And he said, oh, okay, this is how you do it. So every time he has an answer. So after the presentation, you should think about which questions you want to put to Lyosha and send your questions to the chat. And please rate the presentation and send your questions using this QR code. Good luck with the talk. Thank you. Okay, let's start. Today's presentation will be dedicated to the profiling. Surprise, surprise. This track discusses languages and tools. We have already had a talk on compiler. Obviously, if you have a language, it must be compiled. Sometimes instead of a compiler, you've got an interpreter. You wrote a code. After that, usually you have to debug it. So you must have a debugger. And usually somewhere in our toolbox, there is a profiler, which not many people are clear on. What is a profiler? A profiler is a tool which we usually do not need. And we start needing it when we run into problems. It may be a problem of performance, for instance. The machine is slowing down. Why? And then you remember about the profiler, and I usually tell people that before you run to grab a profile, first you need to identify the source of the problem. After you've done that, then you select the right profiler. Although all profilers do more or less the same thing, they are all different. For different languages, for different situations, you may need different profilers. So we've got a problem with performance. And first you need to localize this problem somewhere. Picture this. A web app, the users complain, impossible to use, it's extremely slow. It turns out that the browser is somewhere in the browser build, so we shouldn't be optimizing our backend. It's the browser that should be optimized. So okay, after we are clear on the front end, and we localize the source of the problem in the back end, the queries are coming in, the response is provided, and we see that there is a big lag between the incoming requests and the outgoing responses. It looks like the lag is too big. Now, this is a task for us. There is a code which processes a request, spends time on this request, and we think that it spends too much time. We need to understand what's the problem, where is the issue inside the code. Where is this time lost? And this is where you should run and grab a profiler. Different platforms, different languages have use for different profilers, but there is one versatile method of profiling which is represented everywhere, and it's something that you need to start from if you know very little about the problem yet, and even have very little idea about the code, who wrote it, and what's inside. It's called a sampling profiler, or the sampling profiling technique, which is the topic of this talk. So you take a pretty profiler, you initiate it, you profile, you collect data. You see a lot of numbers, tables, multicolored pictures. How to make sense of this? A question is not a banal one. When I first encountered profile in Java, I ended up writing my own because I could not make the top and bottom of the Java's one. So it is a good idea to actually understand how profile is run. Over here you see a screenshot from a special profiler. The Periscope profiler, they've got a demo. It's a continuous profiler. It supports pluses and Java and Python. So I suggest you play with it if you have free time. So to go back to our task, we've got a code and we need to localize the performance problem in this code. The code has classes, methods, procedures, maybe statements. And in all the megabytes of the source code, we need to find the bits and classes and methods that must be explored in order to fix the issue. This is the task at hand. We must find or evaluate or understand which code runs faster or slower as the code processes our request. So, how is the code executed? There is a flow, one flow. There is time. Time passes. The request comes in. The flow recursively calls functions. Usually, code processing means a chain of calls, and as a result, you get this timeline. A request comes in, calls, parsed, processed, database, response. So you can represent it as a timeline. If you ever did profiling of front ends, this will remind you of this picture. This is a Firefox profile, if I'm not mistaken. It's the same thing. When you analyze performance in the browser, virtually this timeline as is built, and then people explore it. In the back end, things are slightly different. And there are different approaches required to analyze this picture. How does profile in the backend happen? What's the difference between the browser and the backend? In the browser, we start getting into panic when the loading takes a second. In the backend, we start getting into panic when request processing takes hundreds of milliseconds. In the browser, it's one page. In the backend, it's hundreds of thousands of requests per second. So we can't generate a timeline for one request. Instead, we do it for a chain of requests. At discrete points in time, we take stack traces, and we have a set of samples. After we've got a set of stack traces and samples, we do not care in which order they actually were generated. Then we work with this information statistically. And how do you do this? You have to group this data, and there are two approaches to that. You can group samples by the method that was at the top of execution, or you can group them from the point of flow entry. And this is how you get two main representations that the profilers will operate. In the second case, this is going to be a calls tree. It will start growing from the entry point, and then it will branch out, and then we'll see on every branch some statistical frequency associated with it, the probability. If we do it in the opposite manner, we'll get a tree of hot calls, or sometimes it's shown as a histogram of hot calls. What's interesting here is that if there is a method that is constantly on the stack, we see it all the time, it will be there the thickest. And on this tree, then you will be able to understand how you've reached that point. After you sorted everything out and grouped it, the information is added to the tree, it's represented as a tree. Every node of the tree can be labeled with a weight, which will be the same as the number of samples that this path on the tree contains. And out of this weight, we will then visualize the tree. Over here, like you see a schematic of a tree and a screenshot from the Java profiler that looks very, very similar. This is the second screenshot from Pyroscope this time. And what's important to add here is profilers love to draw milliseconds or seconds everywhere. In fact, the sampling profiler, in sampling profiling, you do not have the time as such, because your initial data samples just the number of samples, not the time. So you can sample for a period of a minute, 140 cycles a second, so you should have 6,000 samples, but you see that 3,000 samples went through request processing. It means that 50% of them are still hanging somewhere. So profilers, what they like to do is they multiply the number of samples by time. They normalize everything to seconds, milliseconds, and it's only confusing everyone. There are many reasons why profilers will want to distort this information, especially when it converts from samples to seconds. But almost all profilers do that, unfortunately. And another thing, every frame has a self-time column. What is self-time? There is a tree. Ingot node has two subsidiary nodes with weights 1, and well, Ingot has a weight of 3. It means that once there was a stacked trace where the self-time was once, it was seen once at the top. But if you never saw it, the number will be 0. Usually when we look for the bottleneck, we want to start with the elements that appear the most at the top of the stack. My slides do not move. Now they move. Very well. So we sampled and profiled and visualized everything. First, we start with the hot methods histogram. At the top of this histogram, we see the methods that we saw most often during sampling. It means that they have the highest probability of being executed and consuming resources as our code was running. The question is then, how does a method end up in the top? It can be in the top if it takes several seconds and it's very slow. Obviously, over several seconds, we have collected many samples, and all the samples will see the challenging method. Or if during those several seconds it was indeed called 100 million times, and although it's super fast and is executed in microseconds, just because it was called too often, we see it too often at the top in the samples. That's why, I mean, it's important to understand, because in samples you will not be able to differentiate between the frequent and the slow methods. In sampling, the sampling will not tell you anything about the absolute execution time, absolute runtime. In profiling, never ask the question of how much time does this task take. What's important for you to understand is how much of the time of your task. No, what is the percentage of the actual calculation, say, in your task in the overall time taken by processing your request. I hope you understand the idea. You know what you expect from the sampling profiler. The hottest methods will be at the top. Okay. We've got Java, Pluses, Python. Everywhere they have sampling profilers, and they work somehow. How do they work? For a profiler to work, we need to collect a stacked trace, and we need to schedules the collection of data collection of stack traces, and then depending on how you schedule that, you will get this or that report. Stack traces. So it's a compilable language process, and the compiler produces a binary code. Its program stack is generated. You stop the execution of the code. You interrupt it. At the stack, you see the current execution point. Then there is a projection. You can use indicators and pass along the stack and collect the whole chain of calls. For every call, you will be able to get an address where the call came from, and then from the stacks you'll be collecting the addresses of instructions of the binary code. But we're not interested in binary, we're interested in the program code. For one thing to convert to another, we also need the table that will show us the method name and the string number. These conversion tables may not come out accurately from the compiler for various reasons. The compiler can do terrible things, change the order of lines. So there is always a possibility of getting inaccurate information, and the lines that you will see in the sampling profiler report may not really correspond to the actual code that was executed. So your hot place actually may be somewhere close to the line that the profile will show you, but it will not be that line. So that's the string. That's typical of C++ and Rust and Go. Binary is compiled there, then symbols table is compiled, or information for the debugger. There is also interpretable languages. If you try to collect stack trace from an interpretable language, you will see the code of the interpreter. No Python code at all. And then there are some strange languages like Java or JavaScript that can interpret and compile, and even there are head compilations. There's some other options. You collect a stack trace, and somewhere you see compiled code, somewhere interpreted code, and there are compiler optimization and advice and whatnot. So you need to have platform support for good quality of stack traces, and sampling profilers should rely on the runtime opportunities. Java has its own mechanisms, and JavaScript too, Python, Ruby, they are all different mechanisms, slightly different, and the tools will be different. But eventually, when you've collected the stack traces, the two main methods of analysis will be the same for all languages. But this makes things interesting for us. So once again, the code that you see is not the code that is run on the physical processor. And to try to get accuracy and the number of the string out of the profiler is a bad idea. So yes, you should be guided by these results, but you should first and foremost rely on common sense. When the profiler runs, it can produce you the applicable code, then the runtime of the execution environment. With the pluses, it's easy. These are libraries. In case of Python, Java, things are more exciting because they have their own virtual machine, which has its own complicated functions. And tricks. So on the stack, you will not see the applied code. Instead, you will, for instance, see the virtual, the code of the Java virtual machine. Or sometimes the code is executed at the level of the core, and you start reading from the file, and then at the time of sampling, something happens on the core. Or nothing may happen. And
важный критерий, по которому профайлер...
One important criterion that differentiates between profilers is which code they can handle. Our code can be run, like here in this case. We are waiting for the next request. During this method, the code is not run on the CPU core. It's waiting in line. But then the request comes, it's run, it's already on the core. So some profilers will take samples only from the code that is executed on the core. Others will read everything in the system, everything that's executed on the core at the moment, all the ones in line. And in the second case, this is called the wall clock testing, and the second one is called on CPU testing. What if your bottleneck is the database and you are profiling your app with a profiler that tests the on CPU code? Will you be able to learn anything useful? Okay, moving on.
Помимо того, что код может ждать, код может выполнять.
The code can wait. The code can be run on the CPU. The code can await the CPU. All the CPUs are taken. And the code should be run, but it's waiting in line because all CPUs are busy. Or it can be scheduled.
Произошло прерывание, поток.
The code can be interrupted because it's waiting for the page to upload from the drive. And voluntary waiting. They are requests, like in voluntary requests, in terms of stack trace, you will see some wait for something, or
даже если мы stack-trace в этот момент снимем, мы там ничего не увидим, потому что это может быть просто блокировка на доступ.
If it's SIG-fault blocking, then probably even if you capture stack trace, you will not see anything. And where are the slides? Okay, it's here. The slide is back. The slides are on the screen. What does this lead to? We must sample. We must take 100 samples per second, but what we end up with 33 samples because it's the wrong code of the virtual machine, or not the wrong code, but we got to the virtual machine with our code at the wrong time. And then you have to make an estimate as to how many samples you are using during profiling. If you see that you are losing too many, you need a different profiler, or maybe you need to investigate why you are losing so many samples. Maybe that's where your problem lies. The simplest thing to do is to collect samples n times per second. This is what is called wall clock sampling. Why doesn't it work? Technically, we can collect samples that are run, that are executed. If you use perf, Linux profiler, which is a wonderful thing, a powerful thing, but it only sees the flows that are executed at the moment. The ones that are waiting in line are ignored. Okay, so it works on a schedule. You set 100 hertz frequency, it takes 100 samples per core if something is run on the cores. But there may be other options. You can sample by time, by clock. You can also sample by memory allocation. You've got Java, you've got pluses, and we need to understand where all the garbage is coming from. And in the JVM, you can sort by intensity of memory allocation. Per every 10 megabyte of allocated memory, we take one stack trace. This is also a powerful tool if this is your problem. In Sharp, sampling by memory works well, but sorting by CPU doesn't. And many colleagues say that if your problem is in Sharp, first you enable allocation, and then if there is an issue in allocation, this is where your bottleneck is. In Java, this is not always the case. but it's still relevant for Java too. In addition to memory allocation, in Perf you can also sample the second-level hash misouts. These are specific events for that particular tool, but if you go deep into this story, then that's one of the options how you can fine-tune your sampling to your specific problem. You will be able to identify the types of events for sampling that will represent the problem better. Next. Like I said, the two main views of data from sampling is calls time or a tree or a histogram of hot calls with self-time and total time separated. We are in 2024. In this year, everyone who is anyone in performance is designing flame graphs. A flame graph is a tree with all the nodes with assigned weights or normalized by weights. The sixth layer is at the bottom, then the branches grow out of this bottom. If the branch has a little weight, it becomes next to invisible. If it's thick one, then it's an important one. You start analyzing an unknown app and you build a tree. To understand the tree, you need to click all the way through the tree. It can be wide and deep and whatever. It's not always very convenient, but in the flame graph, you will immediately see a pattern. Even if you don't see anything, not a single pattern, you will understand that there is no pattern there.
So that's a flame graph, and there is a screenshot of a flame graph built with my tool. And this flame graph immediately shows several typical plateaus. That means that it took some significant time to complete. Oftentimes, you build a flame graph and you see this. Don't try to discern anything there. It wouldn't make any sense. How come? What was the reason? That's the app that has the front-end stack in the back-end. What do we mean by that? That's template mixed with the business work. And so what we have is a flame graph, then the stack, and above that is the crown of the tree with all the heavy calculations that are spread all across the crown of the tree, and that is why we do not see them visually. What do we do about this? You might recall that we deal with statistics. I'm going to speed up, but I hope that I'll be able to drive the message home. Let's say we have a set of samples, and we can process the HTTP requests. That's our data set. This is the set of samples that will be used in processing the requests. In the JavaScript, there will be another million flows that we don't care about for now. Then we use the hot method histogram and try to link it. Let's say it's GDBC, then we get a weight coefficient that would be 1, hibernate another link, another weight, so it's hibernate. In JDBC, that means that the stack reaches JDBC and stays there. If we see hibernate but don't see JDBC, then we put 1 against hibernate. And that's the way we follow the entire, we populate the entire diagram. Sometimes there are several pathways to the hot method, and that requires additional analysis to better understand how many facelet compiles we have, and so on and so forth. Everything is then summed up, and you get the number of samples. And we get the number of samples that are relevant for each of the subsystems. For instance, if your request processing is 100%, then you can split it into the amount done in the database, the facelets, and so forth. And the process of populating the table could be finished if you reach 20%. I don't work with a table that often. I have my own automation tools to this effect, but the idea behind that is basically the same. Ultimately, what you get is a beautiful image like that. Moreover, if you need to generate a beautiful report on the optimization, you can normalize this diagram with the average request response time, and this is an example of one of my cases when it took us 8 weeks to accelerate the Java monolith about 30 times. No, hold on a second, just less than that, but there were other problems as well. Anyway, it was accelerated by an order of multitude. And every time we identified the bottleneck, analyzed the code, discovered problems, and moved on. This is a report for people who pay us, but sometimes it's useful for your own self to take a look at the report. Right, to sum up. The sampling and profiling technique is a very versatile and useful technique that you should be proficient in. Sampling profiler exists for any programming language, for any front end, and you can go to a totally foreign project, see a foreign code, and you can get data and draw some conclusions based on that. More complicated techniques require pre-analysis of the code so that the profiler can be directed to a specific analysis domains. Sampling can also help you regulate all overheads, one sample per minute or several dozen samples per second. Sampling profilers can be applied in production as well. However, keep in mind that if you use it, you have to know how your sampler works. Is it a non-sample? What are the limitations? For instance, in JV, there is the Javafied reporter. It's a great profiler. It's a built-in awesome profiler, but it has lots of problems. For instance, if you're inside the JVM, it ignores a sample. If you run the native code, it ignores the sample. So the number of samples acquired is very specific. And before you make any conclusions, you need to double check how come it happened this way, and do we really need to use the accentuating profiler, or should we use different tools? So simpler profilers such as Visual VM in Java are more understandable and make more sense for the first phase of the analysis. Keep in mind that data is going to be distorted because the addresses that we get from the stack are not 100% match to the code stacks. For many reasons, that happens for many reasons, because the compiler changed the position of the code lines, or maybe decided that characters should not be generated for every line so that the file is smaller. And ultimately, instead of 10 points per meter, you get just 3. In other words, the lines that were recorded in the table of symbols by dots are not going to be visible. Well, how do we, what should our attitude be? Well, you should be skeptical. A sampling profiler cannot answer the question of how many methods were used. You should have request logs at the very least. Let's say you deal with HTTP requests, 80% are JDBC, but 80% of which. So you use logs to get direct response time, and then convert it with the help of direct measurements. So the profiler will not help you on that. But otherwise, it's a powerful tool both for primary analysis And as I already mentioned, if you're patient enough and if you have Excel spreadsheets, you can investigate even more complicated cases. That brings me to the end of my presentation. Please send your feedback to my QR code. You can subscribe to my blog and subscribe to my organization. That's the TimePad. From time to time, I run workshops on Java and JVM, and you'll find much interesting information on how to work with JVM and profilers. And you can email your questions to me too if you've run into issues with profiler performances. And you also offer profiling training courses. Yes, I do, but you know, they're not done on a regular basis. So subscribe to TimePad and you'll get the most recent information. By the way, this is the only training course that received only positive feedback, so you're awesome. Thank you. Let's move on to the questions. It was not a hardcore presentation. I still remember my name. So question one, how do we properly profile a hybrid environment with a hypervisor, a power virtual driver when part of the code is processed in VM, then is and then it is sent to a hypervisor and then sent to the host of the system? Wow. That's a very interesting question. Why the question? Why are you asking this question in the first place? Before you answer the how, you have to understand the goal. Are we optimizing a hypervisor? Are we optimizing an app? Are we trying to solve a problem that is relevant for this hypervisor? I've never come across problems like that, but the you know, if you use a host, then the perf can activate and sample this chain with the help of the hypervisor. But this is a difficult case, and I don't think you should use a sampling profiler, but rather specific special tools. Right. The next question. Much depends on who's asking, right? Right. Let's move on. What will happen if the profiler sampling frequency is lower or equal to the serial team frequency? How do we sample them? Because it's a high probability that you will see lots of runtime frames rather than your code. That's true. Let's take an ideal case. It doesn't matter what is happening. If your sampling is ideally spread over time, then you'll see everything. The problem, though, is that for multiple reasons, the sampling times are not evenly spaced apart. They are shifted. So, if we're talking about JVM and the built-in stack trace mechanisms that are synchronized amongst themselves, then I would say that a perf would be a better option because it will sample the data set and demonstrate all the errors. We will see some internal JVM functioning, and it will also be difficult for us to play back the symbols, because on Java script it works more or less well, but if we use Kotlin, then it's going to be a nightmare. I don't know how to marry a sampling profiler and Kotlin, because Kotlin has its own stack tracing mechanisms, but they are underperforming and they're not useful for sampling. Therefore, we need to localize the task. If we're looking for a low-level problem, then it's a perf. Then, if you're looking for an app problem, we probably don't care what is happening inside. Right. There is. Everyone is calling profilers providers. Either it's T9 or people misunderstood your presentation. So What if we really need to? Can we use profiler in the risk architecture, or is that impossible? What's the problem with the risk infrastructure? I'm not clear on that. I've never dealt with the risk infrastructure, but I think standard perf would be your sufficient option.
Более-менее нормально и Linux поддерживается.
Linux supports the risk architecture, so maybe this question deserves a clarification. Right now, I'm not clear what the question is. Well, Igor asks the following question. How come a profiler cannot just instrumentalize the code and insert a lightweight logging when you enter or leave a function? For instance, I write a thread in a local buffer, I enter a function at this point of time, and then it could be flashed to a flash disk, and that would be the end of the problem. Well, the answer is a yes.
Профайлер так умеет. Просто когда вы запустите вот этот вот профайлер с легковесным логированием, вы внезапно обнаружите...
Well, the lightweight logging will slow down your app 100 times, and there is a chance that because of certain timeouts of external requests, it will be unable to operate. And then if you do that, you'll get data on the way the slow app was executed, and 99% is overhead of the lightweight logging, because the number of events is going to be too high. Intel CPUs implemented it in hardware. It works. And I even attended talks of people who told everyone how they use it for Java. So it exists, use it, but it's complex. You have to set it up properly, you have to deep dive into that, so it's by the virtual machine, because you would need access to the CPU, and yeah, well, I think it's way easier to sample it. Right, let's move on. We have a maniac here in this room, and he's asking, can a profiler be activated in Brody? I would say not only it can, it should be activated in Brody. And you have to use the sampling profiler because the advantage is that you can control the overhead. And, you know, you can set it up, you can get 100 samples per second, that's one overhead, or you can set it up in such a way so that you get one sample per minute. And over a week, you will acquire sufficient statistics to be able to analyze it for some bottlenecks. And I experienced things like that, and the results were quite positive. So at a point of time, I identified a very interesting behavior of the code during production with the help of a lightweight sampler. It didn't result in any problems back then. We discovered the error and fixed it. Right. We have two more questions. They are down-to-earth questions. It's great that you are using simple language finally, and now even I'm clear on what you are saying. When do you need profiling? Is it when the performance goes down, or is it a constant, an ongoing process in production? Oh, sorry, in development. Well, a development processes might differ. Some companies have testing departments, some run testing on users, some have performance departments, and they write performance tests full-time, they fine-tune performance and so on and so forth, while other companies don't even have departments like that. There are different approaches, different software programs, different requirements. And I believe that at the very least, every developer should know how to use it if the necessity arises. Because when the necessity arises, you won't have time to learn how a profiler works. It's desirable to have everything on hand. But overall, if you can start analyzing performance with the help of a profiler as soon as possible, because when I started projects from the scratch, my performance tests were run during the first MVP. Right. Got it. Let's take another question, and then we'll select the best question. Well, how heavy an app becomes if you include a profiler, and does it result in additional costs, additional resources, and so on? That should be done on an experimental basis with your app. There is a Java file recorder. It's built into the JVM. It works off the shelf, and default settings will give you an overhead of 1 to 2%. However, if your app architecture abuses exception, and that happens quite frequently, and in the background you have 1,000 to 3,000 exceptions which are suppressed, and this is not an error, this is the way the code was written, then it will turn out that if you activate Java File Recorder, it will just fail. Because Java File Recorder tries to compile all the exceptions, and there are too many of them. So much depends on your settings, the way your code was written. So play with it, experiment with it. You can always fine-tune it so that the overhead is not that high, but we cannot say that our tool always gives you an overhead of 2% and not more. We can't guarantee that. Well, actually, there are lots of questions that we are unable to answer right now. Let's just... there are some strange things that I see here. Now, pro divers, providers, anything but profilers, I guess. There are things that you never even mentioned in your presentation. Now, I guess you know what the difference is between all these things. Alexey, what's the best question out of the ones that you answered?
А какие вопросы были?
Let me try and recall the questions that were addressed to me. It's always difficult to pick the best one. There was a question, actually.
Давайте отдадим приз человеку, который хочет профилировать.
About profiling in hypervisor. I believe that this deserves the prize. This person has a great has great mind. Right. There is our winner.